So again, for the first one, the complex conjugate was 4 plus 5i. If you multiplied the two together and you FOILed, you would get 41. Okay, your middle terms would cancel out. 4 times 4 is 16. You would get negative 25i squared, which would change to positive 25. 16 plus 25 is 41. All right, so for the second one, we had to get rid of the complex number in the denominator. So we multiply 2 minus 3i, okay, by numerator and denominator. I'm going to skip a step. In the bottom, we're going to have 4 plus 9. So in your denominator, you have 13. Sorry, I forgot, had to add there for a second. In the numerator, we get 10, negative 15i, negative 2i, positive 3i squared. So this is going to change to a minus 3. 10 minus 3 is 7. Negative 15 minus 2 is negative 17i over 13. Okay, so that's one way you could type it, but I asked it for it in standard form. So that would be 7 over 13 minus 17 over 13i. Okay, or if you wrote that out, 7 divided by 13 minus 17 divided by 13i. All right, any questions there? All right, so obviously it didn't happen here, but again, I think we saw an example yesterday. If you can simplify these fractions, do that. We always want it in the most simplified form. All right, so our last complex number topic is actually finding complex numbers. Where is the page? What am I doing? Here we go. Okay. So, like I said at the beginning of this, actually, let's see if I still have that graph. No, I don't. Okay. So some of our quadratics, so as you know, the things that we've gone over, a quadratic is, it has the second degree. So by definition, it is going to have two solutions. Now, those solutions may be real. If they're real, they cross the x-axis, okay? But our parabolas don't always cross the x-axis, okay? Sometimes, they're floating in one quadrant. They're either all above or all below the x-axis. When we have this, we still have solutions, okay? Okay, but our solutions will be imaginary. Okay, so that's where we get our complex solutions from. Yes, we want to do that. Okay, so remember, we can get our imaginary solutions from the famous quadratic formula. Okay, negative b plus or minus the square root of b squared minus 4ac over 2a. Okay, so the principal square root of a negative number tells us that if we take the square root of some negative number a, we can rewrite that as the square root of a times I. Now, some places write it like this, and usually that's how it goes, with the real number part first, followed by the imaginary I. So you kind of treat it like a variable, right? So if you had x there, right, the x always comes last. But if you did write it like I times the square root of a, that's fine as well. They mean the same thing, right? That's our symmetrical property of multiplication. Okay, so let's just kind of take this into practice first before we move on to actually finding solutions. So here we're going to simplify the square root of -3 times the square root of -12. So there's a few different ways that we can do this. I don't know if you remember from algebra, if we multiply two square roots, right, as long as they're both square roots and one's not a cube root and the other is a square root, okay, essentially what we can do is we can multiply what's underneath, right? But here we have a problem because they're both negative, all right? So the first thing we always want to do is remove that negative from underneath the radical, the square root. So you would rewrite this. Okay, I'm going to put parentheses just to keep things organized, as the square root of 3 times I times the square root of 12 times I. Now, what I do when I do something like this is I'll add a little end of the square root, okay, just so you don't get confused, that the square root doesn't go over the I as well. Okay, so it would end there. All right, and taking the square root of I, that's a whole nother, that's crazy. We won't be doing that. All right, so here, now that that negative is removed and these are actual numbers, right? They're not nice numbers, the square root of 3 and the square root of 12, but they are real numbers. Okay, now we can simplify and multiply. So we do this with our radicals. So the square root of 3 times the square root of 12, 3 times 12 is 36. Again, we treat these like variables. So I have an I times an I. So that's going to get us I squared. So when we have something like this, we always want to break this down. Now this is nice because this is an actual square root, right? The square root of 36 is 6. Now the I squared, remember that equals -1. So 6 times -1 is -6. All right. So the square root of -3 times the square root of -12, even though both of those things aren't real, okay, not in the sense that they don't exist, but because they're imaginary, okay, when we multiply those two terms together, we in fact get an answer. Now, I do want to say be careful, okay, I did earlier, make sure you take those negative square root out first. If I just went ahead and multiplied this, the square root of -3 times the square root of 12, well, that would just get me positive 36, which would be 6, okay? That's not the case, right? It doesn't just equal 6. All right, we have to pull out those imaginary. That gets us a -1, which changes the answer. All right, so again, make sure you pull out that I first. All right, let's look at one more simplify example, and then we'll move on. Okay, so this involves two types of simplification. Well, the first thing we're going to do, right, is we're going to pull out that negative. All right, so we pull out the imaginary number from both of those radicals, and now I have the square root of 48i minus the square root of 27i. Now, the difference here is we're using subtraction. I can't add two radicals together unless what's underneath the radicals is the same thing. Okay? If it's the same thing, then we treat it like a variable, and we just have two of those things. Okay? So, the square root of 2 plus the square root of 3, I can't combine those. I have to leave it like that. Or I plug it into a calculator and I find the decimal. But moving on out here and in AP Calculus, this is much more accurate than saying, 2.15, some number that goes on forever. So most of the time we just leave it like this, okay? Square root of 2 plus square root of 3. Here, okay, we can simplify it because they have the same thing underneath the square root. So there's 2 square roots of a's. Right? So we just have 2 times the square root of a. So we want to try to get these to have the same radical. Now, how you guys simplify radicals, I'm not sure how you've done it in the past. There's multiple ways to do it. I like making a tree. So I'll show you that method. When I'm done, you can say, hey, Mr. Murray, I don't know what the hell that was. Can you do it another way? And yeah, I'll do it another way. So I'll break up the 48. So somebody tell me two numbers that multiply to 48.
7 and 8.
7 and 8.
I'm going to say 6 and 8.
Yeah, 6 and 8. Oh my God, sorry.
6 and 8. Oh my God, sorry.
That's okay. Right? And then we're just going to keep breaking these down as far as we can. 6 is 2 and 3. Those are both prime numbers. I can't take that any further. 8 is 2 and 4. The 2 doesn't go anywhere. 4 is 2 and 2. Then I look for pairs of numbers. So I have a 2 and a 2 here, and a 2 and a 2 here. So this method is a little confusing because this pair gets brought out as 1, right? Another way you can look at it is, you could take the square root of 4, right? And that gives you 1, 2. So when we break the 48 up, we have a 4 on the outside because I have 2 groups of 2. And then I have a 3 left over, so that 3 stays underneath the square root. Another way you can do it is find numbers that multiply that are squares, right? So the square root of 48 I can rewrite as the square root of 16 times 3. Well, the square root of 16 times the square root of 3 gives me 4 root 3. Okay, so like I said, there's many different ways that you can simplify radicals. If you have your own method, if it isn't one of these two methods, and you get the same answer, that's great. If you need more practice with that, let me know, and maybe I'll do like, a side extra credit worksheet.
Mr. Murray,
What's up?
can you do like another example?
Okay,
Like
so
just
let's do
like
20. Let's do 27.
Okay.
Which method do you want to use? Do you want to use the tree method or the factor method?
Use the tree method.
Okay, so what are numbers that multiplied to 27?
3 times 9.
3 times 9. So right here, you can kind of do this, right? So the square root of 3, you can't find that. But the square root of 9, what's the square root of 9?
3.
3. Okay, so 27, the square root of 27 is 3, because we found that whole number, times what's left over, times the square root of 3. So actually, okay, we're running out of time, so this will probably be one of the last examples I do, but what I'll do is I'll put some simplification extra credit over the weekend. So it's not mandatory, but if you do want to practice that over the weekend, then you can do that. I know it's probably been a while since you've seen this kind of stuff. Okay, so we found out the square root of 27 is 3 times the square root of 3. And again, we just bring the I along for the ride. Now, these have similar parts, right? Here I have 4 square root of 3 times i's. Here I have 3 square root of 3 times i's. So I'm looking at these coefficients out here, and that's what I'm going to subtract. So 4 minus 3 is 1. And then I still have the square root of 3 times I. So my final answer would just be the square root of 3 times I, because you don't need that 1 there.
Wait, so we don't do I squared?
Nope, because we're not multiplying. Because it's just addition or subtraction. Okay, you only get I squares if you're involving multiplication in the problem. All right, let's do one more of these. I think we should have time. No, I don't want to do that one. Oh. All right, so let's do the square root of -8 plus the square root of -50. All right, so first thing you're going to do is, if there's a negative, automatically pull out that imaginary number. All right, so we made what's underneath the radical is positive, and we have the imaginary number on the outside. So now 8, what can I break up 8 to? 4 times 2. All right, let's throw the square root over both of those. The square root of 4 is 2. And I can't do anything there, so I'm going to leave that underneath the square root. So the square root of 8 is the same as writing the square root 2 times the square root of 2. So that becomes 2 times the square root of 2 times I. So now let's break up 50, and now let's try to remember, or try to find a number in 50.
25 times 2.
Well done, right? Because at 25, that's a nice square root. Right? The square root of 25 is 5, and we have that square root of 2 left over. Well done. Good job. So now, again, we just have to look at just the coefficients now because this matches this part. Okay, square root of 2 times I, square root of 2 times I, those are the same. Right? If you want to, you can kind of use a substitution method, right? You can say the square root of 2 times I equals, some number y. So this would rewrite as 2y plus 5y. So when you add those together, right, we don't have y squared. We would just get 7y, right? Or substituting that back in, we have the 2 plus 5, that gives me the 7. And then we still have the square root of 2 times I. Now, the reason that I want to make sure that you guys get this is that when we use the quadratic formula, this is going to come into play. Okay, not so much maybe where we're adding two things together like this, but simplifying it to make it as simplified as it can be, which makes it easier for us. All right. Any questions about our operations with negative square roots?
Nope.
All right. So just a reminder, if you did plan on doing any more extra credit, that's due at the I'm going to say it's due by 2:30 because grades have to be in at 3 o'clock for me. I will put an extra credit that goes towards the second marking period on just simplifying radicals. That'll be due Monday or sometime next week.